So today I will introduce a far-reaching and flexible toolbox of directed distances in the sense of divergences, or you may call it disparities or dissimilarity measures between quantile functions of two probability distributions P and Q. For those who are more into finance, you could also call the quantile functions as collections of value at risks. Okay, we apply this new toolbox to obtain a novel toolbox also to solve Kantorovich type optimal transportation problems. And at the end, I will show you that we flexibilize at least some well-known Wasserstein distances we have already seen today. So I start first with to explain a little bit about the divergences or directed distances between two probability distributions, okay, first. Later on, we will apply to quantile functions, okay? So divergences between probability distributions are well-known tools in statistics, machine learning, and artificial intelligence. They're used for parameter estimation, testing for goodness of fit, Bayesian decisions, pattern recognition, blah, blah, blah. So a lot of applications. Yeah? The question is how to measure a directed distance between two probability distributions, okay? So prominent examples are, well, the phi divergences. We have already seen it today. In particular, the Hellinger distance, the chi-square distance, the total variation distance. Okay, that's one family of divergences. And the other family of divergences are what I call the classical or ordinary Fragment distances. In particular, the L2 distance, we have seen it already before. And of course, the Kuhlberg-Leibler information or relative entropy, which actually it belongs to both families. Also, the very recent density power divergences. Okay, so I promised you to deliver a toolbox. So we will have divergences between P and Q, and the toolbox is reflected by different choices of a generator, phi, and a scaling m, yeah, which is a non-negative measure. Okay. So for the moment, let's say that the two probability measures P and Q have a lambda density P and Q, and also the scaling measure should have a density with respect to lambda. We call it small m. Okay. So if the dominating measure lambda is the Lebesgue measure, then P, Q, M are classical densities, where m may be not normalized, okay? So think, for instance, here for on Gaussians for P and Q. If lambda is the counting measure, then P, Q, M are classical mass functions or frequencies, okay? So for the divergence generator, we basically assume at the moment, yeah, that it's continuously differentiable and strictly convex, okay? And for the moment, phi lives on a domain of the positive real numbers, okay, for the moment. So I would like to explain you the scaled Fragment distances, which we developed a few years ago. It works like this. So the main part of the integrator is phi evaluated at the ratio between the density P divided by the density M by the scaling, okay, minus phi evaluated at the other probability density divided by the scaling density minus phi prime evaluated at Q divided by M times the difference of P divided by M minus Q divided by M. So that's the main part of the integrand, and the other part we use again the scaling M here, but of course this is a non-linear thing, okay? So, of course, in order to guarantee that this stuff exists, you need proper conditions, and this was even further generalized by Michel and myself 2 years ago. And basically, it's really a divergence, so it holds that it's non-negative per construction. You will see in a moment, and it is zero if and only if P is Q. Okay, so that's the definition of a divergence. So for the moment, let me explain. If lambda is the counting measure, okay, then everything gets to a sum over the finite states, okay, finite amount of states. And I'll show you a picture. Yeah, okay. So here we have to generate the phi, okay, and we have say here 4 states, okay. At each state we take p of the first evaluated at the first state divided by m evaluated at the first state, and also for q. So let's take the q here. At this point, you take the tangent line to the function phi, to the divergence generator, and at the other point, you evaluate the gap between the function and the tangent line, okay? So then you multiply by the scaling m again. You do this for every state, and you sum it up, and then you end, okay? So per construction, this is non-negative, okay? You can see here it's more or less already intuitively that it's zero if and only if P and Q coincide. Okay. Yes. A special case, of course, we have heard in several talks, are the power type divergence generators. So the generator is basically a function of the power alpha. Yeah? And if alpha goes to 1, we end up with the generator of the Kullback-Leibler information divergence. And if we let alpha tend to 0, you end up with the generator of the reverse Kullback-Leibler generator, okay? So this leads, if I plug in this and then do it for the scaled Fragment distances, we end up what Igor Weide and myself called the scaled Fragment power divergences. A very important special case is the case alpha to be 2, then the divergence generator is t minus 1 squared over 2. Yeah? So now, what we changed? So far, I've told you how to measure the distance between two probability distributions reflected by their lambda densities, okay? But now we switch the context. What do we change? Yeah? So first of all, we take a divergence between quantile functions, okay, of P and Q, yeah? Okay? And further differences are now the dominating measure, we integrate over the Lebesgue measure. So basically, we evaluate Riemann integrals, okay? And one important thing is, as we all know, the quantile functions may become negative. So we have to flexibilize the domain of the effective domain of the divergence generator phi. This is done by interval a to b. So also the next change is that phi need not be strictly convex, but convex. And it may not be differentiable. If it's not differentiable in the formula as above, we don't take the derivative, but uniformly with a factor c as subderivative. So this is just a linear combination, well, a convex combination between the right-hand derivative and the left-hand derivative. Okay, but we take it uniformly. The c does not depend on it. Yeah? Okay. So what else do we change? Instead of the scaling m, in one scaling, I split it into 2 scalings, and I make those adaptive. So the scalings depend on the quantile functions themselves and nothing else. So where W is a kind of a weighting function. Okay? So, and then we end up with the following divergence. Huh? So we integrate over the Lebesgue measure, and the integrand is upsilon. Yeah, it has this form. Yeah, you see now we have 2 weightings, yeah, or 2 scalings, yeah, instead of 1, and the psi is actually as before, but here replaced by the subderivative. Yeah, and the scaling is with the first W, okay? And then, of course, we have to have a little bar on it. That means these are the extensions on the boundary, okay? So we need this. So under some technical assumptions, yeah, we can show, well, by construction, this is non-negative, okay? And under some technical assumptions, we can show the reflexivity that it's really zero if and only if the two quantile functions coincide, Lebesgue almost sure. So now to go to mass transport, yeah, we have to use an additional requirement, and that's the very well-known condition of quasi-antitone, and I'm happy that Pierre has already mentioned. There are several other names for this, so submodular, lattice subadditive, two antitone, two negative, delta antitone, super negative, and satisfying the Monge property. It's very nice because if you walk out here, the Rue de Monge and Place Monge is quite close to here. Okay, so and for this we now consider the Kantorowicz transportation problem, where this psi function, epsilon function here, we've just defined, is the cost function. Yeah. So it's the cost function, it's non-negative, yeah? Okay. So here we end up with this theorem. You can see here, maybe let's start in the second line. So we take the minimum over all probability distributions with marginals P and Q, and of the integral over epsilon integrated over the probability measure, and then we end up with the integral over the epsilon function integrated by the upper Höfting-Fréchet bound, yes? And then we can make a further step and now evaluate things. So the integrand will be the epsilon function evaluated at the two quantile functions, yeah? And here again, I recall the formula we had before explicitly, okay? And then we end up as a total cost with the divergence between the two quantile functions. So, put into other words, okay, the divergence, yeah, is the total cost of the of optimally transporting P to Q with the cost function epsilon. Okay. Well, here are some, and so we explicitly solved the Kantorowicz transportation problem for the cost function epsilon, and the minimal total cost is the divergence. Yeah? And this is usually typically straightforward to compute. And this contrasts, the epsilon contrast, basically very much to the cost function used for the Wasserstein distances. However, there are some overlaps, and I'll show you in the next example. Namely, if you take the divergence generator to be the absolute value of t minus 1, if you take the c to be a half, if you take the first weighting to be v, so the second component, the other weighting to be the absolute value of the second component, then you end up with the cost function, the absolute value between u and v. So you are at the one Wasserstein distance problem, okay? And if you take phi to be, if you take phi to be this quadratic function I showed you before, and if you take the scaling to be just 1, identically 1, you end up with the cost function u minus v squared half, and you end up with the other Wasserstein distance. Okay, so but that means since these are special cases, special cases, so our new divergence very considerably extends these two Wasserstein distances. So, and it's nice things. I only read now the last lines because this is the essence. Here you can see more or less the proof. Each phi divergence is the total cost of an optimal transport problem. each, since you need some strictly convexity-wise continuously differentiability, in a sense, only some small restrictions on phi. So that's why I put each under. Yes. So the next thing is, each Fragment divergence or each classical Fragment divergence is the total cost of an optimal transport problem. So just the formulation of the Cantor-Ridge problem as a definition of a kind of divergence was used recently by Lin and Q, but they restrict P and Q to have a compact support, and they just state it as a problem. They don't give connections to quantile functions, and this means they have no explicit solution. They do it more or less numerically, but they concentrate on applications to GINs. Okay. So second last slide, also now extending these things. Remember, we have the scaled Fragment divergences, and these cover both the phi divergences and the classical Fragment divergences. And again, one can show that each scaled Fragment divergence is the total cost of an optimal transport problem. And of course, you can also, under some assumption on B, that if B does not give multiple points, you can even end up with a Monge transportation plan. Okay? So that's it. So I introduced you a quite far-reaching and flexible toolbox of directed distances between quantile functions. We applied it to the Cantor-Ridge type optimal transportation problems. And in particular, we flexibilized some well-known Wasserstein distances. The references you can find in my conference paper. And so thank you very much for your attention. I would like to stop here.